Hello and welcome to Statistics. Today we're going to be looking at the 5-number summary. In particular, we're going to be studying the quartiles, Q1 and Q3, in the context of the median. We're going to crack open a data set here from Open Intro Data. We're going to be using the mammals.csv data set. First, let's download it using these commands that I prepped here. These are familiar commands. We'll download the file and use read CSV to produce a data frame. If we want to have a look at the data frame, then it looks like this. So this data frame involves body weight and brain weight for lots of different animals here. There are 62 mammals represented. They're all mammals. We also have a gestation period, which is the time that it takes to carry a newborn animal to term on average for the animal's pregnancy. So that data is available for 58 of these mammals, and that's what we're going to be digging into this time. So what we want to do is we want to use the tools of Jupyter, and then we want to understand what they're doing to explore what are the various kinds of gestation period that we have here, and to figure out how we want to organize them. So the first question that we might ask ourselves are, what is the shortest and longest gestation periods? That's a natural question here. You can see some in the 600s. These are in days, of course, and you might notice that the very longest gestation periods are for the elephants here. The min and the max can be calculated this way. The max gestation period for mammals in this data set is 645, and that's one of the elephants. That's one of the elephant species. The min gestation period is 12 days, which I find amazingly short. It turns out that that gestation period is from the North American possum, which has an especially short gestation period because it's a marsupial. This indicates there are 58 data points in this list. Apparently we are missing data for 4 of these guys. Okay. If we want to have a deeper look at the data, notice that we're not seeing all the data here. There's a ... I'm going to use this sort of homebrew command, show values, which won't work in your context, to just have a look at all of these things. And you can see here that there are some very short gestation periods, 2 particularly long gestation periods, and then a whole smattering in the middle. At first, I thought this data set did not include humans because I listed them. They're listed alphabetically, and I scanned them. The data for humans is here, and it's recorded as an average of 267 days, but it's recorded by the name man. So I was looking under H for human or Homo sapien, but it's actually recorded under the name of man here, which I find a little funny. Anyway, it's listed 267 days here, which is a little bit shorter than the 40 weeks that we all learn. But it all depends how you count. And there's natural variability, of course. So these are all the data values. Now, how would we organize them? Let's look. So this is one data view, I suppose. But if we want to have a better idea how the data is organized, then we probably should be looking for some plots. So I want to illustrate 2 kinds of plots. One is called a swarm plot, which we haven't done in the classroom, and one is called a distribution plot, or a dist plot. So let's have a look at these things. We're going to produce those plots. This is a swarm plot. It's just a simple dot view of all of the data values. The vertical axis means absolutely nothing here. All the data values are just kind of smashed out on a line as dots. It's slightly easier to read than this, but it basically is just displaying literally the values of all the data. But we can see a lot from this that might be harder to view from the numeric view here. We can see that the data is very much all smashed up in this region. So the bulk of these mammals in this data set have a gestation period between about 0 and about 80 days. And so those are probably the smaller mammals in the data set. And then a few mammals are out here in these intermediate range, and then just the 2 species of elephants in the data set, have values out here. We can see the same kind of trends when we look at a distribution plot. So the distribution plot naturally breaks this data into ranges of about 100. Actually, the ranges are slightly less than 100 here. So the ranges are about in the hundreds in width. And we see that between the 12, which is the min, and about 90 here, we have this huge spike, which indicates that there is a lot of data in that range. There are 30 of these 58 mammals lie within this range, their gestation period being between 12 and about 90. Then the values drop off slowly until we get out here at the max. So this shows a very unequal distribution. Many values here, fewer values here, very few values here, with a substantial gap here between about 450 and about 600. Now, the inspiration for quantile level thinking, median, Q1, Q3, the inspiration for this is to divide the data into equal collections, to subdivide it. So if you were going to portion out the data for analysis here, you take some of the data, you take some of the data, you take some of the data, you would want to divide it evenly. And the idea of the 5-number summary, including Q1 and Q2, or the median, and Q3, is that we will subdivide the data into 4 equal portions. Now, there is a subtlety here that everybody needs to appreciate, because it's very easy to misunderstand what is meant by subdividing the data into 4 equal portions. I want to talk to you about the wrong way to think about subdividing it, and then talk to you about the right way to think about subdividing the data. If we have data that stretches from about 0 to about 600, then one way to imagine subdividing the data into 4 equal ranges is we could divide it by these values. We could cut it in half at about 300, and then we could cut it in quarters at about 450 and about 150. So this would divide the data range of values into 4 equal parts, from 0 to 150, from 150 to 300, from 300 to 450, and from 450 to 600. That would subdivide the range of data values into 4 equal parts. But notice that it wouldn't subdivide the data itself into 4 equal parts. The larger range from 450 to 600 and change would contain only 2 data points, the elephants, whereas the smaller range from about 0 to about 150 would contain almost all of the data. So there is a difference between subdividing the data by its data range into equal parts in the data range, and subdividing the data by the number of data values into equal numbers of data values. So the other thing that we could imagine is let's take the 58 data points and round that up to 60. We could take the 60 data points and we could subdivide it into 15 data points, 15 data points, 15 data points, and 15 data points. And notice that that would play out very, very differently here. We would go from 0 to, I don't know, only about somewhere in the 20s or 30s by the time we would read out 15 data points. And the 15 data points at the top would include the elephants, but lots of these data values too, and would go all the way down here into maybe the 200s range before we had read out 15 data points at the top of the range. So subdividing the data by the range of values from 0 to 600 is a very, very different proposition from subdividing the data by the count of the number of data values that we have. So which one do we want to do? For the purpose of calculating the median and the Q1 and the Q3, we want to think about that latter subdivision. We want to take the data values by count and divide them into 4 equal parts, which have the same number of data values in each part. And if we do this by computer, well, I'll show you how to do it by computer, but first I want to talk to you about how do you do this by hand. So that's why I listed the data values here. The first thing that we have to do is we have to have a sorted list of the data values. You can produce a sorted list on paper if you like, or using whatever tool you like. If you're working from a sorted list of the data values, then you can just cut that list in half. You have to cut it in half by count, not by finding the midpoint between the data range values and cutting it in half there. If you do that, it would be about 320, and you'd cut it in half right about here. But clearly that's not in half, right? So we don't cut it in half by the data range values. We cut it in half by a simple raw count. So we have to count this. This is actually 58 data points. Half of that is 29, so we read off 29, and I already counted them earlier. So that gives us this. It looks like less than half in this display, but that's because all the 3-digit numbers are out here, and they're longer, physically longer than the 2-digit numbers. So that's 29 data values here. And that's exactly half of the data values. And then from 90 up to 645, that's the other 29 data values. And so the cut point is right in between 68 and 90, and we will find the median exactly in the middle there. So the midpoint between 68 and 90 is 79, and that'll be the median. If we want to find the Q1 and Q3 values, well, the median is also called Q2. If we want to find the Q1 and Q3 values, then we'll just continue further subdividing these things. So we have 29 values here. So these 29 values will then be further subdivided. Now 29 is odd, so when we subdivide that, then we have to be careful. 29 subdivides into 14 and 14 and 1 left over. So we'll identify 14 on the left side of this and 14 on the right side of this, and then the 1 left over will be the 15th. So we just have to count out here until we get the 15th data value, which I don't remember what it is, but give me a second. So that's 12, 13, 14, and the 15th data value is there. That's 35. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, just checking my work. So 35 here is the 15th data value. And the reason I'm selecting the 15th in particular is because I have 29. I'm trying to exclude 14 on the left side, 14 on the right side, and pick the middle one, so that'll be the 15th. So I'm reasoning that the 15th data value is going to be this 35. So this, just as this 79 cut location evenly divides the data into two equal halves, equal not by data range, not by a long shot by data range, but equal by count, this 35 further subdivides the data ranges, subdivides the data into equal portions by count and divides it into quarters. Okay, we can do the same thing over here. We can count out 14 values and find the 3/4 point here, which will be one of the data values. Let's do that next. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and the 15th here will be this 210. So the 210 is the 3/4 way by data count. Notice that it's nowhere near the 3/4 way by data range value, right? This data range stretches all the way up to 640. So the 3/4 mark would be up near 480. But we're marking Q3 here as the 3/4 point by count on the data. So this is how we calculate not only the median, but also the Q1 value and the Q3 value by hand. We simply subdivide the data at the median, we identify the left half and the right half, and then we further subdivide those halves, producing Q1 and Q3. So those values, those three values, Q1, Q2, Q3, evenly divide the data into 4 equal portions. Now there is a little bit of a sticky hang up here that causes us a little bit of grief if the original data set works out to be odd. If there had been 59 data points instead of 58, then when we calculated the median, it would have been one of the data values. And if so, then we would have had to make a decision about how we identify the halves of the data. Do we exclude that value or what? So the most common thing to do here is if the median is one of the data values because the original data set is odd in count, then we exclude it when we refer to the left half and the right half, and we just calculate the median of the halves as usual. So that's how we subdivide the data. If students, in my experience, if students make a mistake calculating Q1, Q2, and Q3, it's because they're reasoning about the data range division instead of reasoning about the data count division, which is a very different way of reasoning. So let's see how we can visualize the answers to these questions. The first thing I'm going to do is I'm going to just use the describe command because the describe command produces all of these calculations. Now you might notice, here's a little bit of a surprise. I said that Q1 was 35, but Python is reporting that it's 35.75, which isn't even one of the data values. And I said that Q3 was 210. Python is reporting that it's 207.5. Okay, so yeah, that's how it is. So there are different policies for how people count in the cases that these numbers don't work out even, and how people adjust. And what's happening here is Pandas behind the scenes is following a slightly different policy than the one that I am using. So I would urge you to not worry about the difference here, and let's just pretend that it says 35 and 210. So these numbers are the 5 that we've calculated in this lecture so far. We've calculated the min gestation period to be 12, the max gestation period to be 645, and we've calculated Q1, Q2, and Q3. Now, before we go on to a graph of this, a plot of this data, I'd like to talk about why we would compute these things, why we would compute all of these 3 things, and how we would use them to understand the data. So the median is a kind of middle, right? It's not exactly the same as the mean, but it is a kind of middle. The reason we would calculate the mean to be 79 is, the median to be 79 is if we're looking for some idea of what is typical. What is a typical gestation period for a mammal, right? Obviously, there's a lot of variability all the way from 12 to 645. So there is no typical or normal that everything needs to be close to. But if you're trying to just get a handle on what is a fairly ordinary gestation period, the median is kind of the best measurement that we have. So 79, the median, or Q2, should just be regarded as kind of a typical middle value, right? It's not a value that actually occurs in this data set, but it's kind of a central value here. So the purpose of Q2, or the median, is to give us a kind of a quick notion of what's typical or central in these values. What do we make of Q1 and Q3, which divide the data further? Well, Q1 is here. It is in the perfect center, by count, of the lower half of the data. So the proper interpretation of Q1 is that it's really a read on, among the smaller data points, what is a typical small data set? Is typical small data value. So you might say, okay, among smaller mammals, what's a typical gestation period for a small mammal, right? What's a typical low value for a gestation period? 35 is certainly not unusual, certainly not remarkable. It's kind of middling among the lower half. So it's kind of a typical low value here. The remarkably low values are here, and these two are both species of possum. So this is kind of a typical low value. And that leads us to Q3, right? Q3 is the median among the right half of the data. And so it's a typical high value. Q3 is telling us, 210 is telling us that among the larger mammals with the longer gestation periods, a typical gestation period for a mammal with a longer gestation period is about 210 days. And that's, not exactly, but consistent with the human experience. It's much shorter than the human by a couple of months, but it's kind of in the same ballpark. So 210, or Q3, it's basically showing us a typical large value. It's not a remarkably large value. It's not like these 400s and 600s in our data set. It's a typical large value. So Q1 tells us a typical small. The median tells us a typical middle. And Q3 tells us a typical large value. And then the min and max, of course, tell us the entire data range. So knowing all of these values together gives you a pretty complete picture of how the data is roughly distributed, right? It doesn't tell you everything, but it tells you the rough distribution if you know all of these numbers. And that's why these numbers together are called the 5-number summary. So the 5-number summary are the min, the Q1, here called 25%, Q2 called 50% here, Q3 called 75% here, and the max. So these 5 numbers are called the 5-number summary. And sometimes we just say, oh, you want to know about gestation periods? Well, I'll just write down these 5 numbers, and then you'll make of that what you can. But more likely, we use those 5 numbers to make a picture. Let me show you, lastly, how to make a picture out of these 5 numbers. using a box plot, but I'm going to complement the box plot with a swarm plot. So let's, I need to color this so that we can still see it. Excuse me. There we go. So here I've overlaid the swarm plot that we had before with a box plot. Let's briefly hide the swarm plot and just focus our attention on the box plot. So the box plot's job is to be a display of these 5 numbers, right? So this vertical line, so there are 5 vertical lines in this box plot. There's this one, there's this one, there's that one there, and that one there, and that one there. And these 5 vertical lines are doing a job, and the job that they're doing is to display the 5-number summary. This one is right at 12. This one is right at 35, or Q1. This one is right at the median, which I think we agreed was 79. This one's right at Q3, which is 210. And this one is supposed to be right at the max. But Pandas is doing us a favor here and automatically excluding 2 of these data points because it thinks they're outliers. So thank you, but no thank you, Pandas. I'd really like that to be continued all the way to here. So let's just pretend this line is here. The upper whisker on the box plot is supposed to show you the max of the data frame, but Pandas is doing its thing by default and excluding the elephants as outliers. Thanks, but no thanks. So, so as a summary here, we learned what the minimum, what the Q1, Q2, and Q3 and max all represent. We learned how to interpret them in a graph. We learned that Q1 represents a typical small value, Q3 represents a typical large value, and Q2 represents a typical medium value. Notice here that the box plot is very far from evenly cut up into quarters, right? If I tell you that the box plot's job is to tell you how the data is cut up into quarters, you might say, well, that's not at all cut into equal portions, right? That's not fairly distributed. It's not fair in data range, and this is a picture of the data range. It is fair in terms of data count. Even in this tiny region between this vertical line here and this vertical line here, there are a quarter of the data values. And then in this very small region here, another quarter of the data values. This very, very long region out here has only a quarter of the data values. So it does not divide it evenly by data range value. It divides it evenly by count. And that's the job of these quantile stats. All right. Have a very happy day.